All right, so this R function is the rate of change of the snowfall, but the question is going to ask me to find the depth of the snow. And so the tricky thing is I don't have a function here. They didn't give me a function for depth. You need to create your own function. So sometimes if they give you a function that is describing a rate of something, you might need to create a new function that describes the total of something. All right, so the rate of snowfall is this. Let's create a new function d of t, which is going to be the depth of snow at time t. All right, and then we can say, if we can find our notes, we can say that that rate r is d prime. Okay, so then we can say for this problem, so what else can we say actually about this problem? We could say some other things about this problem. So this is our rate. Here's what else they give us. So they don't give us how much snow was, they don't tell us there was no snow on the ground to begin with. There might have been snow on the ground to begin with. All I know is that at 6 a.m., somebody woke up and recorded the total snow depth at 8.7. So what I know is that d of 6 equals 8.7. All right, so remember I had to create this function d for the depth of snow so that I could record that information. At 6 a.m., the snow is 8.7 inches, so d of 6 equals 8.7. All right, now it says, the first thing it actually says here is use technology to determine, use technology to make a graph of the function on a window -1, 13 to -1, 4. So all right, that's easy to do. So we just go and let's look at my y equals, I already put in, this is our r of t. These other functions are for different problems. So let's turn them off for now because I'm going to want to leave them in there, but I'm going to turn them off for now. And let's look at a graph. And by the way, I set the window -1 to 13, -1 to 4, just like it says to do in the problem. And then I graphed it. And this is what it looks like. So we started out with no snow falling. The snowfall increased, and then it hit a maximum. But remember, this is not the depth of the snow. This is the rate at which snow is falling. Okay, so now it says to do this, so what I would do is snap a picture of this and include it in my homework when I turn it in, because this is going to be homework. All right, now it says use technology to determine the maximum snowfall rate, the maximum rate of snowfall. Well, this is the rate. So if I want to find the maximum, and I'm using technology, so this whole thing, not all the problems say use technology for all of it. This one's calculator active. We want to really use our calculator to the max on this one. All right, so I want to find that max. So I go second calc, and I want maximum. Right, so just calc the maximum that way. And it asks for a left bound and a right bound. So I'm going to move my cursor slightly to the left of the maximum. That's going to be my left bound. I press enter, and it accepts that as left bound. Now I'm going to move my cursor using the right arrow slightly to the right of the maximum and press enter again. And these little arrows are telling me, they're confirming that I'm going to look for a maximum in between these two x values. And that looks right to me. It asks for a guess. So I'm going to move my cursor to where that maximum appears to be and press enter, and I get the maximum is 6.00014 and the time is 3. All right, so if I used technology to determine the maximum rate of snowfall, that maximum is 6. Let's use correct units. It says here inches per hour, so 6 inches per hour. That's the maximum snowfall rate, which is pretty hefty, by the way. And the time it will occur at, that would be the, oh, I lied. I completely lied. The y coordinate is the rate. So the maximum is 3 inches per hour. And the time when that occurs is the x coordinate, which is 6, at 6 a.m., which happens to be the same time that it was spotted. All right. So that's using technology. All right. Now write an expression involving an integral that will predict the depth of the snow at noon. Now this is where the power of this technique that we're doing is, that I can use the C and D, I can find how much snowfall there will be, how much the total snow is at any time. Once I know the rate of change and I know the amount at any one time, I can use that to find the total snowfall at any time. And that's the power of this. So if I take my equation that we have, this accumulation equation, this one, this is our key for today that we want to remember. All right, so if I put that in terms of my function d of, I'm going to go ahead and keep it very abstract. D of b equals d of a plus the integral from a to b of d prime of t dt. Now what you want to think of is that this d of a is an earlier value and d of b is a later value. Now, by the way, it doesn't have to be, and there are ways you can algebraically change that around, but let's not go there yet. All right, so I want to know the depth at noon, because it says write an expression involving an integral that will predict the snow depth at noon. So I want to know d of 12. Now, what do I already know? I already know that the depth at t equals 6 was 8.7. So I know what d of 6 is. All right, so then my integral is going to be from this value to this value, from 6 to 12. It's from my known value to my unknown value. But you could switch which one's known, which one's unknown too. It all still works. Now my d prime is this r of t that was given, this r of t. It's this function. So that d prime of t is 3e to the negative 0.5 t minus 3 squared. All right, that's my rate, my d prime, which is r, right? This function is here, all right, dt. Okay, so now I've almost written the interval in the expression involving an integral. I need to say what the d of 6 is. It was 8.7, so I can't just leave that d of 6. I knew what it was. It's 8.7. So the depth of time 12 is going to be 8.7, which it was at 6, plus the integral from 6 to 12 of 3e to the negative 0.5 t minus 3 squared dt. So look, what this is really saying too is the depth of the snow at time 12 is equal to the depth at time 6, which is the 8.7 inches that we have, plus however much of this rate accumulated between the hours of 6 and 12, because 12 is what I want to know. This is this 6 to 12, that's the difference between the amount of snow is at ground at time 6 and the amount that's on ground at time 12. Okay, now to evaluate this, we're going to really take advantage of our calculator and everything it can do. For your calculator active sections, you want to be able to do that. It says use technology to evaluate the integral. All of this worksheet is going to be calculator active. Here's how we're going to do that. We're going to take advantage of the fact that I already have that function in for y1. Now I'm going to do a definite integral. I'm going to do this expression right here. Okay, so we're going to quit out of here. And I'm just going to write this exactly like it is. 8.7. Math 9. Math, I can just hit the 9 right now. Or I can scroll down to the 9th one, and it's function integral. Okay, you guys, I think I have at least one person with the older calculator, and I'll show you how to lay that out at some point. Okay, so this is 8.7 plus, oh, I forgot my plus sign. Look at that. So I'm talking about calculator operating systems, and I forget to put my plus sign. There we go. Okay, now the fact that I already put this into the calculator in order to graph it allows me to go variables, y variables, function, y1, and then I just put dx. All right, and this is exactly that integral right there. I just hit enter. There's 14 inches of snow at the end of that snowstorm. How nice. We can go snowshoeing, we can go skiing, we can go snowboarding and everything. Let's put units on there, and that's it for number 1. All right, so next we're going to do number 5. It's a little bit more complicated. If you want, take a look ahead and see if you could formulate a strategy as how you would do number 5. But here's number 1. Let me get this all on here. Here's number 1 all fully worked out for you.